So far we have been discussing symmetric cryptography, and we will review the main characteristics and then start looking into asymmetric cryptography. And from this figure, you can already see in asymmetric cryptography, we are using two keys, the public key to encrypt and the private key to decrypt. This is in case of to ensure confidentiality. Now with the cryptographic standards, so far we have been focusing on this part, the symmetric cryptography. And we have seen some algorithms for string ciphers and others for block ciphers. Now, once we move into asymmetric cryptography, shortly I will motivate why this is important. Suddenly, we can ensure not only confidentiality, but also asymmetric cryptography gives us the ability to address these other security properties, particularly authentication, non-repudiation, and message integrity. So you see here the symmetric cryptography, in terms of capabilities, all it can do is confidentiality. It does not address this very important aspect of security. So, and for the asymmetric cryptography, we have two major families. Some of them are based on discrete logarithmic problem, and others are based on factoring. And by far, the most widely used and the most important asymmetric cryptography protocol and associated algorithms is RSA. Now, for ensuring authentication, message integrity, and repudiation, asymmetric cryptography also relies on hashing and hashing algorithms. We will see this in more details, but just to highlight this to you. And by the way, recently, this is the most important hash algorithm. We will see the details. We will cover those in very lightweight and maybe spend a little bit of time on SHA-3, which is the latest standard for hashing. So this gives us the big picture of symmetric and asymmetric cryptography and how they are linked and what are their capabilities in terms of ensuring security properties. So some of this you are familiar with, others we will be covering. This is just to give you kind of the plan to complete the security picture, is we need to address these other aspects, authentication, non-repudiation, and message integrity. Okay, so let us first start by just revising what really symmetric cryptography is all about. So it allows parties like Alice and Bob to exchange messages in secure way using an insecure channel by encrypting and decrypting. So by encrypting the plain text, sending it as a ciphertext through the insecure channel, the recipient will decrypt it to produce the plain text. And they do this, the encryption and decryption, uses the same secret key. And that's why we call it symmetric, because we have the same key. You see here, this is symmetric. Same picture, same key on both sides. That's why it is called symmetric. Even the algorithms for encryption and decryption are very, very similar, sometimes identical. And this is just to finalize and to really keep this in your mind in a clearer way through an analogy. So if you want to make this put it in an analogy that is easier to understand using a real life kind of scenario, imagine you have some messages that you want to exchange with other party. So what you do, you put it in a box, you lock the box with a lock, and then you lock it with a lock, you have a key to lock it, and then you send it off to the recipient. So the recipient, they have the box, and then to retrieve the message, what they need to do? Open the box. Now to open the lock, they need a key. And guess what? Both parties, the sender and the recipient, they use exactly the same key. Okay? So locking and unlocking uses the same shared key, but the problem here, the challenge that comes with symmetric cryptography is this problem, which is secret key agreement is required. We have to agree on a secret key. Okay, we can either do it offline, which is not scalable and tedious. We cannot, as you know, we cannot send the key through the insecure channel. Otherwise, this defeats the purpose of encryption. So we have to find some ways to share the key securely. We had to wait until 1976 when Diffie-Hellman came up with the Diffie-Hellman algorithm to exchange the secret key. And we have seen this in details last time. Okay. And this is exactly what I just described. So we use some kind of protocol such as Diffie-Hellman to establish and to agree on a shared key. That's what Diffie-Hellman gives us. And then we use the key. If I want to send something secure, put it in the box, lock it with the key, with the shared key, send it off, and the recipient, once they receive it, they can unlock the box using a copy of the key, and then get the message. That's basically the idea of symmetric cryptography, hopefully in a very clear way. Now, this is all nice, but it has some limitations. And these limitations, we are discussing them to motivate the need to move towards asymmetric cryptography. Of course, we are not throwing away symmetric cryptography. I will explain how it works, how we combine both. In real life, we combine both. So we didn't waste, you don't feel guilty, we wasted a couple of weeks discussing things that nobody uses. That's not the case. We use both of them at the same time. In real world, we call it a hybrid crypto system. It combines both. Okay, so these are the limitations. The first thing we have to worry about this problem of key distribution and securely establishing keys. And not only this, if we have many users that we need to interact with in a secure manner, we have to establish a key with each of them. So if we have a network of n users, this is how many keys we need to do secure conversation between these users. If we have, let's say, 10 users, we will need 10 times 9 divided by 2. 90 divided by 2, 45 keys. And each of them will have to manage 9 keys. So it's a headache. Remember, these keys are top secret. If somebody taps into these keys, they break the encryption or the crypto system. So it's a headache to manage these keys. It's a headache to distribute them and agree on them. No, this is not a tick, this is a cross. It's a headache to manage them and distribute them and establish them. It is a headache to keep so many of them. Plus, we only get confidentiality. We don't get other properties that we need for a secure system. We don't get integrity, we don't get non-repudiation. So, this is not enough. We need to have some better crypto system that will address some of these shortcomings and give us a full solution addressing as well the integrity and the non-repudiation, and the integrity, the non-repudiation, and the authenticity. Okay, so welcome to the asymmetric cryptography. Okay. So again, we start with the idea. This is the idea of the asymmetric cryptography, is that the idea here is the public, anybody can use your box. Let's say you have a box. People can put messages for you there, and only you can open the box to retrieve them. Okay? Maybe a more concrete analogy. Is so what you do. You want people to send you messages securely. What you do, you take a box, and then this box will have a lock, but this lock is not closed. The lock is open. Yeah. So people will take your box. You have so many copies of this box. So anybody who wants to send you a message, they will put it in the box, and then they will lock the box. Okay. So anybody can do this. But once they lock, nobody can retrieve the message inside the box except you, because you have the key to do so. So the basic idea here is that you have kind of two locks. One is public, anybody can make use of it, and the other one is private. And you have this, of course, these two locks are related. And what this allows us to do, we no longer need to agree on a key. The key for encryption is already available publicly. Just go ahead and use it, in our case, to encrypt the message you want to send to a particular recipient. And the recipient, they have how many keys to deal with these messages coming in? Only one key, one public and one private, to communicate with anybody out there. Not like in Symmetric. In Symmetric, for every conversation, for every node on the network, for every party in the network, we have to have a shared key with them. So if we are interacting with 1,000 nodes, we have to share with them secret key, which is very tedious. But in here, with asymmetric cryptography, we already solved this problem of two problems we already solved. We don't need to establish a secret key, and we don't need to manage so many keys. We just have one public and one private. And what do we use the public for? For others to encrypt, and then they send us the encrypted message, and we can do decryption. Okay? All right. So not only this, so we can use, now let's, so this is the analogy. So this is the analogy using boxes, but in real life, in asymmetric cryptography, basically what we have is we have two keys, the public key and the private key. And this is, by the way, this is from Wikipedia, this nice little diagram. So, so let's say Bob wants to send a message to Alice. What he does, he goes ahead and look up her public key. It's available, maybe through her website, through some other means. It's public, it's available somehow. We will see mechanisms to make it available later. And then he has this message, hello, Alice. He wants to send it securely. So he encrypts it using Alice's public key. And then once it is encrypted, it gets sent through this insecure channel. Eavesdropper listening to the channel, they can get a copy of the message, but they cannot do much with it. It's meaningless because they cannot decrypt it. So once Alice receives it, she will decrypt it using her private key and get back the plain text. Okay? So you can see here, we don't have this problem of key exchange or key agreement on a key. We don't need to agree on a key. We just have the public one to encrypt and the private one to decrypt. Anyone can encrypt using the public key, and only the recipient can decrypt. And by the way, this public and private key are related, mathematically related. So towards the end of this session, I'll show you what this means. And also, when we establish these two keys, there is a way to do so. We compute these two keys. These two keys are not random. These two keys are computed using an algorithm such as the RSA algorithm that I will show you later on. So I hope it is clear. Now, in a real world application, surprise, surprise, we don't use asymmetric. By the way, another name for asymmetric cryptography is public key cryptography. They are synonym. You can use one or the other. Now, to our surprise, have a look at this statement. What it says, asymmetric cryptography is rarely used for encrypting exchanged messages. Why is that? Because it's very slow. 1,000 times, could be 1,000 times slower than symmetric algorithms. So symmetric algorithms are happy now. We're not throwing them away. They are still there, still relevant. So encryption and decryption of exchanged messages, large files, no, we don't use asymmetric cryptography because it is slow. So what do we use asymmetric cryptography for in real world? So for key exchange. So remember, like Alice and Bob in symmetric cryptography, if they want to interact securely, they need to have a shared key. How do we establish a shared key? Using asymmetric cryptography to establish and exchange a key securely. And also we use it for digital signatures. These are the two use cases we use asymmetric cryptography for. I will explain key exchange shortly, and digital signature I will also explain it, although we will go deeper into it later. Okay, so what do we use digital signatures for? To provide two things: message integrity, to ensure the message did not change along the way, and also non-repudiation. The sender cannot say, no, I didn't send this message. They cannot deny. That's what non-repudiation means. So, because remember, this image here only shows you one side of the picture, which is using the key to encrypt the message. Sorry, using the public key to encrypt the message, using the public key for encryption and the private key for decryption. You can use the other way around. You can encrypt using the private key. You can encrypt using this one and decrypt using the public key. But in that case, you are not trying to preserve confidentiality. You're trying to establish a non-repudiation. So if I encrypt with my private key, and then you are able to decrypt with using my public key, what does that mean? It means the message is coming from me and only me. Nobody can produce that message. You get the idea. So that's what non-repudiation is. See here, the trick, using the same keys, if we use the public to encrypt and private to decrypt, what are we achieving? Confidentiality. If we're using the private key to encrypt and the public key to decrypt, what are we achieving? Non-repudiation. Is clear this idea? Okay, very good. So let us now see how in real world, how crypto systems really work in real world. When you are using your browser and you are using HTTPS to access some website, so what happens is you have a hybrid system. It uses both asymmetric cryptography and symmetric cryptography. So first, there is some kind of handshake in the beginning to say, okay, we will use definitely to exchange these large messages, we will use symmetric cryptography, but we need to have shared key. So what we can do, we can use asymmetric cryptography to establish this shared key. I'll show you what it means shortly. Also, we can use asymmetric cryptography to sign our messages, to create what is known as a digital signature. So that's what we use these asymmetric parts for. And then once we establish the shared key, then we switch to symmetric cryptography because it is fast. And we can do so, we can choose whatever algorithm we want, whether it is block cipher or a stream cipher. Okay, so here it is. This is how it is done in real world. This is an example. So you see here, Bob has a key, and the key is made up of two parts, the public and the private. The public is known to everyone, and the private is secret. Only Bob knows it. Now, let's say Alice, she wants to exchange messages with Bob. So what she will do, she will choose a random key. Yeah? Choose a random key. For example, if they want to use AES, what should be the size of the key? Let's say 128, 192, 256, right? Let's say she chooses the key to be 128. So she generates 128-bit key, and then what she does with this key? Encrypts it using Bob's public key. And then she sends it off to Bob. What Bob does? He decrypts it to get the key. Asymmetric cryptography now is done. That's it. We will not use it for, although we can, but we will not use it for encrypting and decrypting messages that we want to exchange. Why we are not using it? Because it is slow. We have established now a shared key, then we switch to the symmetric cryptography. In this case, we are using AES and then we use AES as you know it. We give it the key, we give it the plain text, it will go ahead and create the ciphertext. We send the ciphertext, and we keep doing this. You see this? So we have asymmetric for key exchange, and then for data encryption, decryption, we are using symmetric. This is how really cryptography is used in the real world. It's a hybrid system. This is just explaining how the key exchange works. Now let me just give you a brief idea about message signature, although we will see this in much more details next session. So here it is. You see, Alice wants to send some message, at the same time send some signature with it. Why do we need to send this signature with the message? For two things, two reasons. What's the first reason? Non-repudiation. What non-repudiation means? Alice cannot deny. Later she said, oh, I didn't send this message. No, you sent it, and this is the evidence. The second thing is, for Bob, when they receive the message, they have confidence that there is nobody on the network has tampered with the message. We protect ourselves against the man-in-the-middle attack. Remember the man-in-the-middle attack? Intercepting our messages and changing them? They cannot do this with message signing. So the way it works, I take a message and I sign it. Signing means, we will see the details, but for now, signing means I take the message, create a hash. A hash is basically squeezing the message into a short little string. And then I take that string and then I encrypt it using the private key. So the hash value encrypted, what we call the encrypted hash value, a signature. And then what do I do with the signature? Attach it with the message. Now the message is up to me. I want to encrypt it or decrypt it. It's up to me. It's not a problem. So in here, I decided not to encrypt the message. It's not critical. I'm just saying, hello, Bob, and here is the signature to make sure it's coming from me. And along the way, it will not say, minnak lillah ya Bob. Okay? Nobody will change it. Okay? So here, we are saying hello, Bob, and we are adding the signature. Yes? Now, once Bob receives it, of course, they get the text. But they want to get confidence. It is really coming from Alice, and nobody changed it along the way. So what they will do, they will check the signature, verify the signature. I'll show you what it means shortly. If the verification passes, then this is an authentic message coming from an authentic source, and it was not compromised. It was as it was sent with zero change. Okay, so this is a little bit more detailed. I just wanted to bring the idea a little bit closer to your mind, but we will go through the details of this later. So this is how we use public key for signature. So what we do here, have a look. We take some data that we want to send. It could be a large file, it could be a big message. We pass it through a hashing function. So hashing is another topic that we will discuss. At the end, it squeezes it in a hash. Maybe you have a 1 megabyte file, it becomes 256 bits or 128 bits. What we do with this hash, we take it and we encrypt it using the private key of the signer. Whoever wants to sign, they get the hash, and then they encrypt it using the private key. And then what we do with this signature, we attach it with the data we want to send. By the way, this data could be plain text, could be encrypted, it doesn't matter. We attach our signature, and then what we have at the end, we have a digitally signed data. So now this is the signature process. Very simple process. On the recipient side, they will do what? They will do the verification process. So first, they will get the data from the message, and they will pass it through the same hash function. And they will produce the hash. Then they'll take the signature attached with the hash, signature attached with the message. Because it is encrypted, they will decrypt it using the public key. And then you will get the original hash, the plain text of the hash, and they compare the two hashes. If they match, we have proved two things. The authenticity of the message is coming from an authentic source. Second thing, we ensured integrity. And the third thing, we ensured non-repudiation. Three things achieved using this very, very simple process. This is heavily used in real world. It's a very, very important idea, which is the message signature. Nothing to do with encryption. This is another, encryption is for ensuring confidentiality. And the signature is for ensuring three things: non-repudiation, authentication of the message, and integrity. You get the idea, yes? But of course, in the real world, you can combine both. Instead of doing here plain text, you could encrypt this one, then hash it, then send the signature of the hash, an encrypted version of the hash. So that's basically what signature really means, but we will see a lot more details later on. Okay. Now, I hope now asymmetric cryptography is clear, and I hope the relationship between what it brings to the table, what are the new features it's brought along, and also I hope the relationship between symmetric and asymmetric cryptography is clear, and how asymmetric cryptography addresses integrity, non-repudiation, and authenticity. Now, one of the algorithms and protocols for asymmetric cryptography, the most widely used one, is RSA. So RSA, it stands for the first letter of the first name of the people who invented this protocol. Rivest, Shamir, and Elderman, and this was in 1977. It is by far the most widely used asymmetric cryptography, although it is being kind of a bit challenged, and there is a growing competition from another alternative algorithm called elliptic curve cryptography. Okay, but we're not covering this in this course, but just for your information. And as we discussed, because this is an asymmetric cryptography algorithm, it is mainly used for key exchange and digital signature, not for encrypting and decrypting, because it is slow relative to symmetric. And by the way, these guys also won the CS Nobel Prize, the ACM Turing Award, because this algorithm is really changed the way we do cryptography. It's widely used. This is by far the most widely used cryptographic protocols. Every time you are using HTTPS, you are using this algorithm. Every website you go, whenever you see HTTPS with the lock on the address bar, you are using behind the scene RSA. Okay, so now let's see. Remember with Diffie-Hellman, if you recall, last time we discussed it, one of the innovations Diffie-Hellman brought along is this idea of using one-way function to provide security. And Diffie-Hellman was in 76, and these guys 1 year after they managed to bring this RSA. So RSA relies on the same idea, that it is based on this concept of a one-way function. So one-way function, you dig into math, and you try to find some function that is very easy to compute, but very hard to invert, very hard to inverse. Very hard to inverse and very easy to compute. So with Diffie-Hellman, they used modular exponentiation that is very easy to compute and very hard to reverse. And the reverse is called logarithm. Yes, discrete logarithmic problem. That problem is very hard. There is no efficient algorithm to solve it. And here, RSA, they didn't want to copy Diffie-Hellman, so they came up with another function. And this time they relied on factorization, factoring large integers. By the way, both of them, they rely on a large integers that are hundreds of digits long, scary integers. Now, here is the idea of factorization. So if I multiply two large numbers, it's super easy to do, very easy to do. But if I give you a large number, let's say I give you this large number here, and I ask you, what are the prime numbers that we have multiplied to produce this number? This problem happens to be a very, very hard problem. And in mathematics, it's called factorization problem. So visually, this is how it looks. I give you these two values, P and Q, and then you multiply them. This is super easy. Then I give you a product, and I'll ask you, what are the prime numbers we use to produce this product? Well, good luck. If you can manage this with large numbers in a reasonable time, very efficient algorithm, we can already prepare the celebration for you for another Nobel Prize. It's a very hard problem. Okay? So the security of RSA relies on what? On this. Once somebody managed to find an efficient algorithm to do factorization, then that system will break, and we have to move on to another system. But so far, nobody managed to do it, so we are okay. Not managed to do it. We can do it with brute force, trying all different numbers, but it will take you hundreds of years. You will not be able to do it in a short time. That's what it means here. There is no. There are of course algorithms, but they have some limits. They can deal with some limited number of digits. But if you have a large integer, you cannot produce this prime 1 and prime 2 in a reasonable time. So that's basically the one-way function that RSA relies on. You can already some questions in here, very important questions, explaining the difference between Diffie-Hellman and RSA. It's important to explore this. Okay, so now let's get into the details of RSA. Here are the details. Now first we need to have encryption and decryption algorithm. The days of using XOR for encrypting and decrypting are gone. In here, we use math to encrypt and decrypt, and some complex math, not complex math, but the operations that are can take a bit of time because these are we deal in here with large numbers. Okay, so remember in asymmetric cryptography we have two keys. We have the public key and we have the private key. So the public key is made up of two numbers, two public numbers. One is the exponent, and one is we use it as a modulus. So the public key will basically have two numbers, E and N. So let's say I have a message that I want to encrypt. I want to encrypt it using the public key. How do I encrypt a message? I'll take that number, raise it to the power of E, and do modulus N. The result is your ciphertext. Yes? Once the recipient receives it, how they will decrypt it? They will take the ciphertext, raise it to the power of the private key, which is a number. Mod N, this will give you the plain text. So this is very simple algorithm to do encryption and decryption. Take the plain text, raise it to the power of E, mod N gives you the ciphertext. Take the ciphertext, raise it to the power of D, which is the private key, mod N gives you the plain text. Yeah? N and E are public. Everybody knows them. D is top secret. Only the owner has it. That is the idea. In here, for this to work and for this to be secure, what are the conditions? D and N must be very, very large. In fact, the currents, like the minimum value is 1024 bits. These two numbers is 1024 bits, but the current recommendation is 2048, or you can even go for 3096. It's large integers. And maybe next time I do a little bit of OpenSSL just to give you how these numbers look like. Yeah? Okay, so this is the encryption and decryption, and here is a small example. So if I want to send the plain text, this top secret 88, what I'll do, and here is my key, here is my public key, here is my E, here is my E, and here is my N, and this is my D, and this is my N. Yeah. So for encryption, I take the plain text, raise it to the power of E modulus N, and this will give me the ciphertext. I send the ciphertext over. The recipient, how they will decrypt? Take the ciphertext and raise it to D mod N. Remember, N is the same in both sides, and it gives you back the plain text. That's it. Very super simple. Now, the next thing RSA gives us, very important, is what else we need here? How do we generate these two? These are not random. These are mathematically related. And the math behind them is quite advanced. Okay, but I will give you like the math version, but in a lightweight way. It's still the full version, but not too much scary details. Okay, here it is. Here is the algorithm, very important algorithm. By the way, you will definitely get some exercise to do in homework and in the exam on this. Very important. This is super important algorithm. Okay, so this is the key RSA Key Generation Algorithm. Super important. Here is my star here. Okay, so what is the output of this algorithm? Two things. Two things this algorithm gives us. One is the public E. The public key, it has the N, which is the modulus, and the E, which is the exponent. And what else it gives? This algorithm produces? Private algorithm, which is B. And by the way, in this course, you also learn how to really write the algorithm in pseudocode. These are very advanced algorithms, but just squeeze them in one slide. Yeah, but behind this, there's a lot of details. Okay, so there is the RSA. These are the Nobel Prize people, how they got their Nobel Prize through this algorithm. This is not something you take lightly. This has changed the way we do cryptography. So what we need, what is the first step of this algorithm? Choose two large prime numbers, P and Q. You know large prime numbers, divisible by themselves and by one, not any other number. Okay? Second step. Here it's easy. Second step, compute N, P times Q. We know now N. You know N, it's part of the private key. It's very simple, it's just the multiplication of both. Now we compute this phi N. We're not going into the details of this one, just take it as it is. Phi N is basically P minus 1 times Q minus 1. This will give us phi N. Then what we do, we go ahead and select a public exponent E, this E here. We select it. We select any number that satisfies these two properties. It must satisfy these two properties. What are these two properties? E, which is this exponent here, it must be greater than 1 and less than phi N. Yeah? And it should not share any factor with phi N, which means this greatest common divisor between E and phi N equal 1. I will explain this through an example. Okay? So you select E. After you select E, the final thing, now we know N, we know E. What is left is D. So D is nothing but the inverse of E modulus M, inverse of E modulus N. Now to solve this, this is the heart of the algorithm. To solve this E modulus N, these wizards, these RSA inventors, they communicated with their friends, but invented something else 2,300 years ago, okay? Which is the Euclidean algorithm. And we use the Euclidean algorithm. I'm not sure you have seen it in any other course, no? No. This is no problem. We will see. So this is where math really helps. We will see. So what I will do, this is the overall what the algorithm looks like. I'll explain it quickly through an example, and next time we go through a more detailed example. But this is the algorithm. D is nothing but the inverse of E mod phi n. And then basically, using these steps, we will be able to produce the public key and the private key. I'll come back and explain these Chinese things once I go through the example. Each entity has its own set of keys. So this is the algorithm to produce the public and the private key. Remember, each entity will have public and private key. Those keys are not random. We just pick up a public key, pick up a private key. It will not work. You need to produce them using this algorithm. And then you take the public key and say to the world, people of the world, here is my public key, but I will never give you my private key. I will keep it hidden. Now these two numbers, basically these are at the end of the day two numbers. How you produce these two numbers? This is the magic to produce these two numbers. That's what it tries to explain. Is clear? Yes? No? Anyway, the algorithm, let me explain it through an example and I'll let you go. Okay, here is an example. Of course, in here we will use very simple numbers. But in the real world, these numbers are hundreds of digits long. Okay, so what is the first step of the algorithm? Pick two prime numbers, P and Q. We picked up P. What is P? 3. Is it prime? Yes, only divisible by 1 and 3. And pick Q, 11, which is divisible by 1 and 11. Step 1 is finished. Step 2, compute N. What is N? P times Q. Now, at least we have one part of the public key, which is N. Now, the second part of the public key is E. How do we pick up E? How do we compute E? We pick up any number. So in this case, E must be between 1 and phi n. What is phi n? Is P minus 1 times Q minus 1. In this case, is 20, which means in our case, E must be between 1 and 20, okay? And it is an odd number. I think I should add there an odd number, okay? So it should be greater than 1, so 1 is out of the picture. Remove 1 out of the way. Then the next one, 2 is an even number. I will not consider it. Then I will move to 3. So let's try with 3. What was the condition for E to be a good number that we can use? It said that the greatest common divisor of E and phi n should be equal to 1. Are you following? Now, this greatest common divisor, in this case, what is E? 3. And what is N? 20. So what we need to find now, what is the common divisor between these two? What is a number, the highest number that can divide these two numbers? What do you think? Now, if you want to find an algorithm to do it, you just need to go 2,300 years ago, and Euclidean had an algorithm to do this. So let me show it to you. Maybe you already know it. So this is the greatest common divisor of 2 and, sorry, not 2. What was the number? 3. 3 and 20. So this is how we do it. We take the highest of these two numbers. What is the highest of these two numbers? 20. And we say 20 is equal to 3 times some q plus some remainder, which means we want to say how many 3s are in 20. How many 3s we have in 20? Is it? 6? 6. Okay, very good. 6. So 3 times 6, yes, plus, this will give us 18 plus 2. This is the first step. Then we kind of do a lift shift. So what we do here, this 3, we move it to the place of 20, and 2, we kind of move it to the place of 2, which means we want to express 3 in terms of 2. So we already expressed 20 in terms of 3. Now we want to see how we can write 3 in terms of 20, which means how many 2s are in 3? 1. And what is left to keep this equation correct is plus 1, balanced. To keep it balanced, we have to add 1. Yes? What's the next step? We do the same. We shift this one to the left, and this remainder will take the position of 2. So another way how to express 2 in terms of 1. How many ones we have in 2? 1. How many ones we have in 2? 2. And the remainder is 0. Once we find the remainder 0, we go back to the previous remainder, and this is our greatest common divisor. This is an algorithm developed 2,300 years ago. It's still in use, very widely used. Cryptography, asymmetric cryptography relies on this. Okay. Now, are we happy with 3? Did we prove that 3 satisfies the condition? Yes? Okay. Now, do we have the public key? Do we have the public key or not yet? We have the public key. The public key is made up of 2 numbers, which are 3 and 20. This is our E and this is our N. Yes? What is left now? The private key. The private key is not a random. We have to generate it in a way that is related to the private key. What is the relationship between the private key and the public key? Sorry? D? I heard it. The inverse. Because what the private key is doing is undoing what the public key did. So the private key is what? The inverse of the public key. Okay? So we have to compute this D. We have to compute this D. And the way we compute D, at the end of the day, D should satisfy this equation. Okay? Should satisfy this equation. What this equation is saying, D times E mod phi n equal 1. Okay, so to solve this equation, what do we need to find in this equation? We know all the variables, we know all the values except D. Yes? We know all the variables except D. So to solve this, again, to find the D from this equation, we go back to the Euclidean algorithm. But this time, we extend it. There is the extended version of this Euclidean algorithm. And then we go through that algorithm. I will show you next time. Unfortunately, we're out of time. We will produce D. I will show you later. We'll produce D equals 7. Let's just try that it satisfies this rule or this law. So what is the value of D? 7. What is the value of E? 3. Yes? Mod what? What is the value of phi n? 20 equal 1. So this value satisfies this rule, so this is our private key. Now how we do this? This is basically using the extended Euclidean algorithm. It's scary, but it's very simple. Similar to this, but once we do this step, there is another step to do what is known back substitution. sorry, just one word. I will let you go and I will explain this later. But these are the details of the extended Euclidean algorithm. I do the Euclidean algorithm and then do the backward substitution that I will explain later, and then you will produce D equals 7. There is a very well-defined algorithm. It sounds scary from the abstract, but if you take an example, go through it a couple of times, like I did, then all the math will come, and then you will start liking math. You will not be scared. It is scary only in the abstract form. You see these symbols, you see these scary symbols, you freak out. But if you go through an example and do it by hand and do a couple of them, then it becomes very, very clear how this magic is working.